So in this part of the talk, I am going to take this whole privacy analysis game to the next level. In the first part of the talk, I was talking about the setting where you actually have the anonymized data set. So somebody like Netflix or AOL or some company publishes a set of records with identities removed, or some social network, but you actually have the data. So now I'm going to be talking about the setting where you don't have the data at all. And what can you learn if you don't have the data? What can you learn simply by observing the system? So you might think that all the problems I talked about in the first part of the talk come from the fact that data is actually released. So, well, one answer that should solve that problem and certainly foil the algorithms that I talked about in the previous part of the talk is, well, how about not releasing the data? Okay, so no data, no problem. And in fact, many modern systems, including systems I'm going to be talking about in this part of the talk, they operate on sensitive data, but they never actually publish it. I mean, data release is fairly uncommon. I mean, this typically arises when somebody wants to run a data mining computation or they want to share information with commercial partners. But in many cases, we have systems that operate on sensitive data but don't actually release it. So this is the setting that I'm going to be working in for the next hour and a half. And here, instead of dealing with an actual data set, we don't have the data set. We have the machine. We have a black box that takes a bunch of inputs. And these inputs are dynamically changing because that's how modern systems work. If this is a little abstract, I'll make it very concrete very soon, so don't worry about it. So we have some algorithm that takes lots of inputs that evolve over time and change over time and so on. And based on that, it produces outputs. And the inputs are secret, so they're never published. And in this part of my talk, I will be talking about how to infer what these inputs are by observing the outputs and how they change over time. And these outputs could be statistics, they could be information based on statistics, and so on. And I'll show this in two very different settings. The settings are going to be dramatically different. In one case, it's going to be recommender systems. In the other case, it's going to be web browsers. Everything is completely different except this basic overarching theme that we're dealing with systems that take some sensitive inputs and produce some outputs indirectly based on these inputs. And as system operates over time, inputs change, outputs change, and how the dynamics of these outputs could be used to infer information about inputs. That's why this part of my talk is entitled The Art of Inference. And the two papers I'm going to be talking about, they both came in Auckland. So one is called You Might Also Like Privacy Risks of Collaborative Filtering, and the other with my students Sum and John is called Memento, Learning Secrets from Process Footprints. Two completely different papers, but what they have in common is this theme of inferring information by observing the dynamics of public outputs. Let's start with recommender systems. As you probably know, recommender systems are really big. So no matter where you go, whatever you buy, you often go to a website and it would have like a little thing there saying you might also like. People who bought these items also bought those items. If you like this article, here are more articles like that. If you want to follow this person on a social network, why don't you follow these other people? So I'm sure you've all seen this, and this is considered a very valuable tool. Some people say the reason Amazon is such a successful company is precisely because they make such great recommendations. Netflix obviously has a movie recommender engines. Hulu, which is a movie watching site, is pretty good at recommending other things. You like this show, therefore you might like that show, and so on. And the way modern recommender systems work is typically using something known as collaborative filtering. That is, they look at the behavior of these users and try to find correlations between items. So they look at what their users buy or watch or express preference for, and then the whole thing goes into some algorithm. And these are very, very sophisticated algorithms. I do not even claim to understand how they work. They've been developed over years and fine-tuned and so on. Very sophisticated. Apparently, the patent on Amazon's recommender algorithms is one of the most valuable patents Amazon has. And based on that, it goes through some data mining magic and produces recommendations. An interesting thing about these recommendations is that you'll notice that in most modern systems, recommendations are what are known as item to item. That is, when Amazon recommends you things, it doesn't tell you users like you liked something. In fact, it takes a particular item and tells you people who bought this item also bought some other items. So this is really one or two steps removed from information about users. So it starts with something that users did, but the correlations that it comes up with eventually are not correlations between users, they're correlations between items. So effectively it tries to find patterns. People who buy diapers are also likely to buy beer, or people who buy a certain set of items are likely to be pregnant. Question? Yeah.
You do, or that's what they tell you they're doing in order not to get seen?
My understanding is that's what they really do. Again, I don't have any insight, but my understanding, they're genuinely item-to-item recommendations based on correlations between items or groups of items. So they produce these recommendations. And here is the problem that I'm going to pose in this part of the talk. Suppose we only have access to this recommendation. Can we figure out individual inputs, individual purchases, and individual transactions that went into it just by looking at recommendations? And this is a pretty tall order here because, look, these recommendations are not based, again, they're item to item. They're removed from users. All I know is that people who bought this item bought some other items. How do I go from that to the inputs that caused this? So that seems a much tougher problem, and trust me, it is a much tougher problem than de-anonymizing some data set that's released here. I don't have any data set here. All I have is the public outputs of the system. And the reason they're public is because they're not considered privacy sensitive. Look, you can go on Amazon, look up any item on Amazon, or you go to a favorite news site, look up any news article, and it'll tell you people who like this item also like those items. You can go to a music listening site, look at any song, and it'll tell you people who like this song also like those songs. Okay, this information is completely public precisely because it has no user information. Yeah.
I think to make it more interesting, Amazon doesn't recommend only based on what you bought there, but also on what they know of you, of what you bought, what you looked in other places.
That's true, but in this case, I'm talking about public recommendations. They're not specific to you. They're not based on your behavior in this case, okay? I can look up an item. I can, clear all cookies. Amazon doesn't know who I am. I can go to Amazon, look up a particular book, and they'll tell you. People who like this book also like those books, okay? So that's not personalized in this particular case, okay? So these are just item-to-item correlations based on transactions of hundreds of thousands or millions of people. So going from that to transactions that created it seems like a pretty tall order. And let me reiterate, these recommendations are item to item. So here I'm going to use American TV shows as an example. And again, here you'll see some show and it'll tell you that, if you like Parks and Recreation, here are some other shows you might also like. And this is based on correlation. So this is just saying that people who tend to like this show, they also tend to like that show. And sometimes even some systems would even give you a raw correlation. There is a programmatic API that'll give you the correlation number. That's very nice. Some are just going to give you a list, and typically this list is ordered. So things at the top of the list are very strongly correlated with this, and things at the bottom of the list are not, or weakly correlated. But because these recommendations are public, this allows for passive inference. That is, what I'll try to do is to be completely passive. Just look at recommendations, and in particular at how these recommendations change over time. So this will be the power of exploiting the dynamics of public outputs. So I'm going to look at how these outputs evolve over time and try to run it back and figure out what are the inputs that could have caused this change in the output. Okay? So it's not these correlations, but by themselves, these correlations, there is nothing privacy violating in it, and there is nothing I can infer from it. Just learning that people who like Parks and Recreation also like Modern Family, like really, there is nothing I can do with it. What I'll need is to watch this over time. And in some of the experiments we did, we had experiments that ran for years. Basically, every day they were watching what this list looked like and trying to see how they evolve over time. It's this evolution over time and changes over time that will provide me with some ability to infer the inputs. All right. So as always, we're going to use auxiliary information. That is, I need to know something about a person in order to infer what they did, and dynamics of public output. So this, it's again, it's the dynamics. It's the temporal changes, that are going to. Okay. So I assume that I already have some information about a person. Let's say I know some TV shows that my target might have liked. Maybe I know, or in case of Amazon, I know some items they might have purchased, maybe based on their public reviews or just by looking at some information. So as before, I assume that I have some partial history about a person. And as always, since these things are very sparse, let me assume, for the sake of the discussion, that this information is uniquely identifying. There are some interesting challenges if it's not uniquely identifying, but let me assume that it uniquely identifies the person. So now my goal is, given this information about a person, can I learn other information about the person simply by observing public outputs of the recommender systems? And again, let me make it very precise. I am not looking at recommendations made to that person. Okay, I don't have access to them. I'm simply looking at public recommendations that the system makes. And these public recommendations are based on lots of inputs, and they're item to item. They're not even related to that user. Okay, they're just correlations between items. For each item, it gives me a long list of correlated items. So how might this work? So let's imagine that's our auxiliary information. This transaction history tends to be relatively unique. Obviously not in the case of shows that a person likes, but I'm just using this for an example. But you know, a set of books the person read, a set of items they bought, a set of movies they liked, yeah, that's pretty uniquely identifying. That was the whole basis of the previous part of my talk. Now, how is collaborative filtering going to work? So let's say there are some shows that a person has liked, and let's say and the goal is to produce item-to-item recommendations. That is to determine which items go together. So suppose Alice watches and likes a particular show. So what do you think is going to happen with the correlations in the system if Alice expresses a preference for a particular show here?
Shouldn't they adapt accordingly?
Adapt accordingly. So how is the system going to adapt accordingly? How is it going? So that's the question. So what is it going to do? Yeah.
The correlation between that show and others that Alice likes will increase.
Exactly. That's, I mean, in some very simplified form, that's all the systems do, okay? You watched like 5 things, then you watch another thing, and I mean, you and all the other users of the system, every time somebody watches something, it increases the correlation and expresses preference for it. It increases the correlation between that show and other shows that person watched. That makes sense, right? So, and of course, this is all happening with hundreds of thousands of users at the same time. So effectively selecting an item, and again, you watch a show, you buy something, makes it and past choices of the same person more similar. Okay, so they become closer together, correlation increases, and somehow in some indirect way, this is going to find its way into the public outputs of the system. So effectively, the output changes in a very subtle, almost imperceptible way. The public recommendations change in response to individual transactions. Again, it's not immediate, it's not direct, it's, you know, there are multiple people doing it at the same time, but somehow there is a very subtle influence that every individual transaction that you don't see has an influence on the public outputs of the system that you do see. So, let's see how we could potentially use this to run this backwards and to infer Alice's transaction. So suppose we know that Alice, and I'm giving it in a very simplified form, obviously here. So suppose we know some shows that Alice has watched, and then someday Alice watches a new show. We don't know this. This is a hidden transaction, okay? I mean, the system knows it, but we don't. All we have access to is the public outputs of the system. What we do have access to, we don't see items recommended to Alice, but typically in item-to-item recommender systems, for each of items in Alice's partial history, we have what? We have recommendations. We have a list of related items. So we can see for each one of them a list of related items. By themselves, these lists of related items tell us nothing, okay? Just if we have a static picture like this, there is nothing we can infer about what Alice watched beyond what we know. But now, and suppose we watch these lists associated with known Alice's history. Watch it. We watch it today, tomorrow, we watch it for a week, we watch it for a month, and there are some changes in the lists. And then one blue morning, we see the following. We see some change. So we see that one of them increased in rank. So what can we infer from this? Yeah, I mean, actually, there is so far not much we can watch from it. Is that like more people, somebody who watched Parks and Recreation also liked The Office, or a few people did, and so on. But the important thing is that by watching it over time, we can see changes in these lists, and we can record it and so on. And in order to infer Alice's transactions, what do you think we need to be looking for? So a change in one list is not going to be enough. Correlated changes. If at approximately the same time, we see all of them changing in approximately the same way. Maybe not all of them, maybe majority, but maybe a particular show increases in rank or appears on like 90% of auxiliary lists associated with Alice. What is this an indication of?
Somebody else watched all this and showed it.
That's right. That's right. Somebody who watched all this watched that. But by itself, it's not going to be enough. Why is it not enough by itself? It could be someone else, but let's assume for the time being that the transaction history is uniquely identifying. Even if it's uniquely identifying, it's not going to be enough. Well, suppose some show becomes super popular. Everybody watches it. So of course it's going to increase in correlation with everyone, okay? So just the fact that something increases in correlation with all of Alice's auxiliary information doesn't tell us much. But what would tell us something? The correlation is limited. That we see some item that at approximately the same time increases in correlation with Alice's, that information that we know is Alice's, but is not increasing in correlation with things that are not Alice's, okay? And this all, and by the way, how do we know it's increasing in correlation with Alice's items? Because for each of these related lists, we see that it's going up in the list or appears on the list, which typically would be caused by increased correlation. Do you get the intuition of how this might work? Yeah, a little bit. So, and we see changes in this list, and once we start seeing correlated change that's limited to what we believe to be Alice's partial history, at this point, we can make an inference. And we can predict that the reason this is happening, the only reasonable explanation for this is happening, is that this item increased in correlation with items associated with Alice, and only with items associated with Alice, or for the most part with items associated from Alice. And what inference can we make from that? Well, probably the reason for this, the explanation for this, given how these algorithms behave, is that this show became associated with Alice. So I hope you get the intuition of what we're doing here. We're looking at public outputs, purely item-to-item correlations. We're looking at several of them at the same time, and we're trying to find correlated change in all of them. And typically, they're not updated at the same time. So when you do it in practice, you'll never see all of them, but you'll see some significant fraction of them. And if you see localized, correlated change in public outputs, you can often make an inference that this happened because this item became associated with a person, and this allows you, and remember, the data set is not released, you're just watching public outputs, this allows you to infer inputs that are normally hidden from you. So sometimes I get this, oh, but isn't this what the whole point of prediction? I mean, isn't this what recommender algorithms do? They predict the show that you're likely to watch. Not really. What we're doing here, as I said, is kind of a mirror image of machine learning or prediction. So predictions seek to impose order on recommendations. They try to look at information from a lot of people and try to say that people who watch one show are likely to watch some other show. Whereas inference is based on temporal changes in this order. So instead of imposing order on predictions, we're looking at how they change over time and try to kind of run collaborative filtering algorithms in reverse and try to figure out what inputs might have caused this change in the public outputs that we observed, and based on these changes, make prediction. So, okay, anyway, I mean, I didn't go into details because the details are complex and it's a little hard to explain why it works and why it doesn't work. I was just trying to use this as an example, kind of how, by looking at public outputs, you can infer inputs. Okay, yeah?
A number of books that give you a recommendation, for example, this one and Amazon and many others. Could you try to figure out using similar technique which of them are talking to each other? Because you know what you did, so you try to figure out, seeing the recommendation, if this information passed along between which vendors.
You can almost see like spread of influence, if you will. Yeah, we thought about this, okay? We have not managed to do it, okay? I mean, these algorithms tend to be a little brittle, so we thought it would be feasible. We have not actually managed to track kind of propagation of influence because we thought we would see this. This person like does this and then he influences other people or those people influence other people. But anyway, we haven't been able to do it. But a lot of these things, I don't know. I mean, these algorithms, we still don't understand why they work and why they don't work. There are lots of techniques in the space that we tried that should have worked and that didn't work, and we can't figure out why they didn't work, in part because we do not like completely understand how these collaborative filtering algorithms operate. But anyway, it's a good idea. I just don't know how to do it. Okay, so any questions about this part? I know I went kind of quickly over this, but this is just to give you a little taste. So let me now try to talk about an entirely different setting, like very different setting, where I'm going to exploit the same idea, which is using dynamics of public outputs to infer sensitive information. And it's only remotely connected to this line of work, but the big topic is the same. And this is this paper called Memento, Learning Secrets from Process Footprints, which was in Auckland last year with my student, Suman Jana. And the setting here is completely different. It's actually about system security. But again, we'll be trying to see what private information can be inferred. So I'm going to be switching gears a little bit on you and bringing you to the world of system security here. And let me just first, as a preamble, say a few words about how modern software is designed. So it so happens that there is this increasing trend in modern software for applications to rely on abstractions provided by the operating system to make them better. So a classic example of that is web browsers. It used to be that a web browser like early Internet Explorer or something, Firefox, this was one big process on the machine that does everything, okay? And what was one of the things that Chrome did to improve reliability? Anybody knows? That's right. Every tab runs as a separate process. In fact, every website you go to runs as a separate process. Even there are multiple. There is one process doing networking, another process doing rendering. So if you look at something like Chrome, for every site, it's going to fork a new process. And it's very nice because now it's not even like you sort of get reliability for free from the operating system. If some website crashes, it doesn't affect the other website you're dealing with, right? Okay, so what does that have to do with the price of tea in China? You'll see in a moment. But the interesting point here is that now somehow this separation between different parts of functionality in browsers, actually in many other processes, is pushed into the operating system. So different parts of functionality run as different processes inside the operating system. So this has lots of good consequences. It provides better isolation, better reliability, better security, better safety. It's just good. But, you know, I'm a security person, so I talk about bad things much more than I talk about good things. Now I'll try to show how this reliance on OS abstractions leaks more information to processes concurrently running on the system. And that's a little bit counterintuitive because you'd think like, well, isolation operating systems, it's been designed over many years, it's kind of very well understood, so how could this be making things worse? Well, there is an interesting facility in modern operating systems, especially in operating systems from the Unix family, and this is called proc file system. Have people here heard about proc file system? A few. So this is one of these weird things. This is like a total legacy of like good old days of like Bell Labs in the 1980s. Okay, so it was designed in 30 years ago when kind of Unix was being developed. You know, when men were men and had serious beards and were power programmers. So it was designed by Tom Killen. Processes as files, published in Usenix in 1984. So this is an interface that allows one process running in the system to learn some information about another process running in the system, even if it belongs to a different user. And why is this facility there? Well, so that I don't know, Dennis Ritchie can help Ken Thompson debug, his programs. Like I said, men were men back then. But interestingly enough, this facility that allows one process to ask certain statistical information about another process, it actually survives in many modern versions of Linux. So you have concurrent processes running on the system, and even if they belong to different users, they can still use this facility to ask questions about the other process. Well, when we started working on this, I talked to some people about this, and they're like, yeah, that's all very interesting. But nobody uses multi-user computers anymore. I mean, that thing has gone away with like VAX machines and whatnot. And that was like a really weird reaction I got from people about like nobody uses multi-user computer anymore because, there are things out there that are effectively multi-user computers. Because on systems like Android, how does it? And that's yet another example of using these OS abstractions for better separations. How does Android use multi-user, this whole multi-user idea? Anybody knows? Every application runs as its own user because Android relies on separation between users in operating system, on standard OS isolation, to hide the secrets of one application from another application, because just like in Unix, you cannot read the files of another user on that system. Same way in Android, one application cannot read the secrets of another application. That's the whole point there. So, in the old days, users were these serious-looking dudes. So now we have other users. So these are what multi-users are today, but they're using exactly the same multi-user facilities in Unix. And in particular, that procfs facility that allows one user to ask questions of the process of another user, it's available to these guys. Anybody knows what permissions an Android process, like a game or anything you want, need to ask questions of another process? What Android permission controls that access? It's a trick question.
Next to is nothing.
Nothing. There is no Android permission because, look, what harm could I'm just asking about some statistics about some other process in the system, okay? What could go wrong here? I mean, I'm just saying, like, how many times it was scheduled on the CPU? I mean, first of all, it's not even clear why it needs to know it, or what's the value of its stack pointer. I mean, these are just kind of ridiculous questions. Anyway, so it's not controlled by any permissions. Any process can ask this of any other process, but it doesn't seem like super harmful. So Right. So, but it's important that sandboxing in Android is based on this standard multi-user Unix isolation. Different apps run as different users. So it's yet another example of using this user abstraction to isolate applications. Okay. So far, so good. But remember, this API for asking questions about another process execution is still unchanged and available to Angry Birds or Dancing Pigs or your favorite application. It runs on your Android phone. It can ask questions of any other process, any other application, no permissions needed. And by the way, this is not just Android. Similar facilities exist in most modern operating systems. They exist in other versions of Unix, like OpenBSD. There are similar facilities in Windows. So it's pretty generic because for various historical reasons, modern operating systems have this, what I'll call accounting APIs. They have APIs that allow processes of one user without any permissions to ask questions about process of another user, mainly focusing on statistics. I mean, you cannot read the guy's files or read the guy's memory. You can just ask, oh, how much memory it's using and stuff like this. And so the question that I'll try to answer is, so what can be learned by having access to this? Okay? So remember, no permissions. So this is so some files are not world readable, but many files in this proc file system are world readable. So what can a zero permission application learn from this API? Well, turns out quite a lot. So some of it is just weird, okay? So this is just odd, that you can read the IP addresses of network connections, okay? That another application is accessing. That's like a big time privacy leak right there, but that's just shouldn't be there. It turns out that the value of the stack pointer could be used for some very interesting attacks known as peeping Tom attacks. So this is the work that was done by Kehwan Zhang at Indiana University a few years back. So that was pretty interesting. But what I'm going to focus on for the purposes of this talk is what can you do with statistics? Because again, remember, like statistics is supposed to be harmless, just like some averages, some sums and so on. So shouldn't be revealing that much. But the interesting thing about it is that you have access to the dynamics of the statistics. So an untrusted process running an Android or any other Unix-based system, it doesn't get just one value of some statistical counter. It gets multiple values over time. So I'm going to be asking what can be done with that. Actually, there was some work last year out of Michigan that showed how packet counters could be used for TCP sequence number inference and for various network attacks. But the one I'm going to be focusing on for the purposes of this talk is this, looking at memory usage and looking at the number of context switches. And this was the work that was done by student Suman Jana. So, and again, this is this general topic. What can be learned from statistics and the dynamic of statistics? So, and memory usage is going to be the most interesting one, in part because it seems so harmless. So that's why the paper is called Memento. So you might remember how the movie from 2000 called Memento, excellent movie, where kind of the whole story is reconstructed in some haphazard way from various snippets of memory. And so that's exactly what we're going to do here. So we're going to have an untrusted process. All it does, it looks at how much memory some other process is consuming. Okay, that's all it's doing. It's just measuring how much memory it's consuming, and it'll use that information to try and infer that process's secrets. Okay, it seems very weird. How can the amount of consumed memory can leak a secret? But you'll see that it will, and it leaks it very well. So let me get a little systems on you and kind of try to give you a very brief crash course on how memory management works in modern systems. So the target here is going to be browser. So remember, we have attack process running, let's say, in Android or your favorite Unix system. It doesn't have any zero permissions. It has zero permissions, doesn't have any special permissions. And concurrently with it, the user is running a browser. They're running as separate users, meaning that this attack process cannot look at browser's memory, cannot do anything. But its goal is to figure out which website the user is browsing without having any special permissions. And what it can do one piece of information revealed by OS isolation mechanism via this procfs file system is the total number of pages of memory that any process is using. In this particular case, it's the browser process, so a concurrent process can always ask how much memory the process is using. And it's going to start by recording this number. And now imagine the user goes to a particular website and the browser fetches a page, and this page is rendered in the browser. So what do you think happens at that point? Well, wouldn't that be nice? Wouldn't that be nice? Unfortunately, it's not so simple. Typically, in order to render a page, the browser would need to allocate some memory. Okay, so what call do you think the browser is going to make? Any systems person here? malloc. It's gonna make a call to malloc. And what is malloc gonna do when the browser asks for memory? Yeah, it's gonna look for some, some free block, and it's gonna give it back to the browser. Is it going to change the number of page counts, the number of pages used by the browser process? Not necessarily. And in fact, if it's a small allocation, it will not. So this change, for the most part, will not be visible through this interface. But sometimes the allocation that the browser asks for is so big that malloc doesn't have enough free memory to do this. And at this point, it has to go to the operating system, to the free page pool, and ask, okay, I'm going to need more pages, and typically this is done via break or mmap. And that will actually cause a change in the observable memory consumption. But so what do you think are the big memory allocations that, like, what causes this? Actually, images, but it has to be a pretty darn big image. Most images are actually compressed, so they're decompressed. But what's the really big thing?
Streaming.
What?
Streaming.
No, not streaming. Streaming typically would be, you just allocate one big thing and you just shove everything into that buffer. So the thing that's like a total memory hog is actually JavaScript, okay? Like it's parsing JavaScript that's like a huge source. I mean, big images too, but parsing JavaScript is a huge source of memory allocations that require so much memory that it forces the malloc implementation. And I mean, different malloc implementations do differently to go to the operating system and do it. But of course, you could say that, oh, wait a second, but doesn't this like sort of non-deterministic, because as things get allocated, deallocated, behavior becomes non-deterministic. So what really helps you here is that if you're dealing with a browser like Chrome, every website starts with a fresh rendering process. So you always start from the same point. So it's a clean slate every time. So anyway, so that's what this process is doing. It's periodically polling this proc file system, and it's recording how much memory the process is using. All right, so I see this dynamics of memory usage. So what is that good for? So here is the amazing thing. It turns out that this pattern of memory allocations actually is uniquely identifying for a large number of websites. Depending on which website the browser goes to, the pattern of memory allocations, the big memory allocations that are actually visible in the operating system, is actually different. So here is the pattern of memory allocations visiting this website called benaughty.com. It's not exactly a safe for work website, but it has lots of images, okay? So, and it goes like this. So allocations goes up, then a bunch of JavaScript comes in and a bunch of sites, so allocations go up, and then some images appear there, and then, and it turns out that this pattern of allocations is very specific to this website. If another website is being rendered, the pattern looks very different. So again, it's this idea how like one allocation just telling me that a browser at a certain point consumes so many megabytes or so many pages of memory, like, so what? But if you track the pattern of allocations, and in some cases deallocations over time, that thing that we call memprint turns out to be like a fingerprint. It's like really very identifying, which allows a malicious process simply by watching the pattern of memory changes, memory consumption of the browser to identify websites. So just to summarize how it works, you can be running your process, let's say on a phone, it's a zero permission app, doesn't have anything, and as the browser is rendering websites, all this app is doing is measuring how much memory it's consuming. It could be polling at a pretty high rate, doesn't need any permissions to do this, and then once it accumulated this fingerprint of memory consumption, it can compare it with a pre-computed database to figure out which website is being browsed by the user. Here is the beautiful thing. These patterns of memory allocation, they're dependent on the operating system, they're dependent on the browser, they're machine independent because allocators in common browsers tend to behave in exactly the same way regardless of the machine they're running on. So that's very nice. That's what allows pre-computation. We did experiments for the front pages of Alexa top 100,000 websites. For almost half of them, these memprints are unique. And of course, you have the standard kind of trade-off between false positives, false negatives. You can tune recognition algorithms to achieve effectively 0 false positives. So that's very nice. So you can set the parameters so that sometimes you cannot identify. But if you declared that you identified website being browsed, you are correct with extremely high probability. You never have false matches or anything like this. So you have uniqueness. And second, you have stability. These patterns of memory allocation are unique across repeated visits to the same page. What really helps you there is this kind of very nice trend in modern browsers to start a separate process for every visit to the page, because you always start from the same place in memory allocation, and your consumption always follows a predictable pattern. So you parse this JavaScript, you render images, and it always creates a very similar pattern. So this picture is pretty illuminating. So here we measure cross-page similarity, and you can see like the stuff across the diagonal. So what do you think is the stuff across the diagonal? So this is similarity, repeated visits to the same page, and the stuff here is similarity to other pages. And you can see there is a region here that's dark along the diagonal and light inside. So what does this tell me? That it's dark along the diagonal and light inside. Dark along the diagonal means what? That visits to the same page produce patterns that are very similar to each other, and light inside means what?
It's a different thing.
That they are very dissimilar to any other page. Okay? Dark dots inside would be false what? Positives, meaning that it's similar to that page. So we have a huge region here which is self-similar and very different to other pages. And again, remember, all I'm watching is just memory consumption and pattern of memory consumption, just some very coarse-grained statistics and so on. So right, so this means that they're similar to themselves. Light inside means that they're different from others. So this really works very nicely. So, and by the way, this is just the tip of the iceberg. You can do much better. For example, once you have identified the site, you can figure out even fine-grained information, because once you know on this website, you can track where the person is going on that website. So I know he's on a particular medical website. Did he go to this disease or that disease? Well, guess what? These different pages produce different amounts of allocation. He's on a dating site. Is he a paid member? Is he interested, I don't know, in boys or girls? All of these different internal pages within the site tend to produce different patterns of memory allocation, meaning that simply by measuring memory consumption, I can infer where the person is going, what he's using. It gets better and better. If I look at dynamics of CPU scheduling and statistics of CPU scheduling, how often the process was scheduled on the CPU, this allows me to break privacy of applications that deal with interactive inputs. Because suppose an application takes input from a keyboard. What do you think happens? So when a keystroke is, when a particular key is pressed, there is a keystroke, it gets scheduled, and while it's waiting for the next keystroke, what do you think happens to it? It gets off the CPU, which means that by measuring how many times it got scheduled, it allows me to measure what? Even better than how many times. It allows me to measure intervals between keystrokes, okay? So I can see like when it changes, this means that he struck the keystroke, and I can actually poll it at a fast enough rate that I can measure intervals between keystrokes. Why is this useful?
Because different keys are different intervals on the keyboard.
Different keys are different intervals on the keyboards, and this allows actually inference of what the person is typing, because based on intervals between keystroke, I can figure out what the person is actually typing. And remember, all I'm looking at is statistics, okay? How often was the process scheduled on the CPU, okay? Through a completely harmless interface inherited by, by modern systems from like Tom Killen in '84, I can effectively infer what the person is typing. I mean, it requires a language model, and there are a few complications along the way, but I hope you see this power of having access to statistics. And this is a general problem which arises again and again, that fine-grained resource usage statistics are correlated with secrets. So because these statistics, because they're perceived as harmless, they're visible across isolation boundaries, they are revealed by most modern operating systems, for reasons because they were used in some ancient past and kind of believed as harmless. Actually, there are legitimate reasons for this proc file system to exist, but there are relatively few legitimate reasons for it to be readable by other processes, except for some utilities and so on. And that actually, just having access to statistics, and in particular to temporal changes in statistics, that is being able to observe it over time and try to kind of reverse engineer changes in statistics, turns out to be a very high bandwidth side channel that allows pretty accurate inference of lots of secrets, like keystrokes, like browsing websites, which websites is being visited, interests on these websites, membership, and so on. So, any questions about this so far? Yeah?
What's the website when loading memory allocation? How does that work with sites like Facebook or Twitter where everybody sees something else?
Oh, right. No, it doesn't work with that, of course. If you see different things, that would be different. But typically, like first of all, here we're identifying the front page, okay? Meaning that, on the front page, people tend to see the same thing unless they're logged in. And for lots of sites, everybody sees the same front page. There is some variation, and again, it doesn't work for all websites. For example, some websites, they have advertising that's so non-deterministic that effectively even repeated visits produce completely different patterns. Some sites look very similar to each other. For example, there are a lot of sites that based on the same template, they produce the same pattern of visible allocation. But empirically, out of front pages of top 100,000, something like 40% are uniquely identifiable, with effectively 0 false positives. So that's pretty powerful. Oh, and by the way, so what's important here is that it's not even if you like start a fresh browser. Even if you're inside the browser and you click on some link and go to some website and memory is sort of dirty, it still works. Why do you think it still works? It's a new process. You click on a website, you go somewhere, it's a new process, okay? So that's the beauty of modern browser design, anything based on like WebKit and things like this, every click, new process, It's good for safety and it's good for us, okay? Yeah?
What about cookies?
What about cookies? If the content changes depending on the cookie being presented, yes, this will not work, okay? Right, obviously, like it has to be stable across. But typically, you'll see that the changes you're thinking about, some image being different and so on, they do not affect this because you're only seeing the effect of really big memory allocations, like some big script runs. It either runs or it doesn't run, okay? And also another thing that helps you there is that sometimes it would start like some plugin, like Flash plugin, and then you'll see the presence of an additional process. This is like a gift that keeps on giving. Okay, good. So I hope this part of the talk convinced you that even if you don't have access to the data, even if all you see some kind of noisy public output, statistics, temporal changes, and so on, in some cases you can run it back and reverse and infer some inputs. All right. So at this point, I'm somewhere like around the, past the half of my talk. Let me start talking about, so this was kind of, the attack part of the talk. Let me start talking about the defenses. And talk about building privacy-preserving systems. And I'll start talking about them now and maybe talk for half an hour or so, and then we'll break for lunch and then continue after lunch. All right? Any questions about this part of the talk so far? All right. Good deal. So now let me go to, let me try now to talk about how to try to build privacy-preserving technologies and try to deploy them or convince real users to use them, where challenges are very different. So in general, I found that breaking things is much easier than actually doing something constructive. So let me tell you a little bit about my adventures in this space. So first of all, one realization that is very important to make for anybody working with data and worrying about data privacy is that we really need to stop thinking about privacy as property of the data. And that's one of the kind of conceptual mistakes that are made by people who work on this data de-identification and data anonymization, things that I talked about this morning. They try to think of privacy as a property of the data set and start thinking about privacy as a property of the computation we're doing on the data. Okay? So that's one important insight. And second is this. All of the attacks that I've shown you so far, certainly like things like Netflix price, social networks, recommender systems, they assume that adversary has some access to auxiliary information. Our experience over the past 10 or 15 years has shown that as far as auxiliary information is concerned, you're only limited by your imagination as to what this auxiliary information might be, and it's very hard to tell in advance what auxiliary information might be. And that's why it's very important for the definition of privacy to be robust in the presence of auxiliary information. That is, somehow when you're trying to define privacy, you need to define it in a way that still remains valid regardless of auxiliary information available to the adversary. So that's maybe one important lesson from all of these attacks that has to be learned. And so far as I know, we only have one such definition that defines privacy as a property of the computation, not a property of the data, and that is robust in the presence of auxiliary information, and that's differential privacy, which is an extremely influential notion that was developed maybe 7 or so years ago, and since then has kind of taken over the world. No matter which computer science conferences you go to, if you go to theory conferences, data mining conferences, systems conferences, now you look at like conferences like OSDI, NSDI, SIGCOMM, kind of hardcore systems conference, they're using differential privacy, and database people are using differential privacy, and machine learning people are using differential privacy, and so on. So it was developed by a bunch of people, Cynthia Dwork at MSR, Adam Smith, at Penn State, Kobe Nissim, Frank McSherry, lots of people worked on it. So I'm not going to talk much about it. I'll try to give a very kind of intuitive definition of it that doesn't use any Greek symbols. This is kind of as simple as I can make it. And this is one of these weird definitions, as I can say what it is, and often people hear things that I'm not saying. Somehow it's kind of one of these definitions where it's on the one hand very precise, and on the other hand, when people try to use it, I often discover that they seem to hear things that are not being said. But anyway, let's try. So this is an attempt to define what it means for a computation to preserve privacy, or in general, any mechanism for computing on the data. It says that privacy is preserved if every output is produced with similar probability whether any given input is included or not. Okay, that seems like a handful here. So intuitively, what is this saying? So it's saying take a data set and a computation, okay? And the computation could be randomized, so we have to talk about possible distribution of outputs. And then if you look at the output of this computation on the data set in which one of the records or any of the records is absent, these output distributions is similar. As a matter of fact, it's point-wise similar, meaning that it's similar. So on every point, the probability, every possible output, the probability of producing that output doesn't change much. So one interpretation of this notion of privacy, and I know it's a little hard to wrap your head around it, and it's just not a super intuitive definition, but one interpretation of it is that if you're trying to convince somebody to contribute their data to a data set, you can tell them, look, whatever this computation is going to be producing, the same output will happen whether you include data or not. So the risk for you doesn't increase much if you include your data in the data set. So that's kind of the intuition here. It's important to mention what it's not saying. It's not saying that the risk for the user, that there is no risk for the user, or that no harm will occur to the user. That's not saying. It's just saying that the same harm of any, or approximately the same harm as any, no, even I'm not saying it right, that whatever harm you're concerned about, it will occur with approximately the same probability whether your input is used or not. Okay, that's what it's saying. It's not saying that the computation hides your presence in the data set. Anyway, it is what it is. So that's the definition, and there is a very rich theoretical framework around this definition that has been developed over the past few years. And that's the only definition we have that's mathematically rigorous. And the nice thing about it is that it holds regardless of the information the adversary has. So it's invariant with respect to auxiliary information. So effectively, if differential privacy is achieved, and I'll show you in a moment how it might be achieved, and describe a particular system that we build that try to achieve it with very intermittent success, that if it's achieved, then it doesn't matter what the adversary knows. So it doesn't matter what sources of information it has. The computation is going to produce the same output with approximately the same, for each output it's going to be produced with approximately the same probability, regardless of what the adversary knows. So whatever the adversary can infer with C's record, including in the data set, the probability of that inference will not change by much, whether the record is included or not. Okay? Sorry, I know it's a little hard to follow. That's as simple as I can make it in 5 minutes. All right. So let's, so as we go on, maybe I'll try to give more intuition on some concrete examples. Anyway, but differential privacy, like I said, it's this rich framework, but these people are theoreticians, okay? So, and I tend to work on more systems side of things. So they're somehow like on that end of the bridge, and I'm on this end of the bridge, and it's not even clear that these bridges connect. Although there have been some very interesting attempts to kind of move this theory into practice. In particular, Frank McSherry at Silicon Valley worked at this system called Pink, which is a very nice system that they released a few years ago, which is designed to be kind of a general purpose system for privacy-preserving data mining computation and for data analysis with differential privacy. So it's nice that we have Pink, but it's possible that Pink is not the last word in this area. And in general, I'd like to, this is the kind of areas that I'd like to work on. I'd like to have a more modern bridge here between theory and practice, and in particular, try to build systems that provide meaningful privacy guarantees and are usable by users who are not educated and so on, or not necessarily educated in privacy, they're educated in their domain area. So for the next half an hour or so, I'd like to talk about one of my attempts to do this. As a matter of fact, we've had several attempts to build these systems and published a couple of papers about it. One was in an SDI a few years back called ARAVAT, Security and Privacy for MapReduce. So that's the one I'm going to be talking about before lunch. And then earlier this year, we published a different system that also uses differential privacy in a very different way. I'd like to think in a kind of more usable way called PyBox. Anyhow, let me talk now. Right, and the difference between them is that ARAVAT is a system for what you might call big data privacy that has large-scale data mining, and it's actually very similar. Its objectives are very similar in spirit to Pink, which is Frank McSherry's system for computing with differential privacy from MSR. Whereas PyBox is a system these are for apps working on individual data, and it's what I'll call small data privacy. So this is for protecting sensitive data in applications that work with individuals, not large-scale data mining. All right, so let me talk about Aravat now. And this is our attempt to marry differential privacy to modern computing technologies. Well, I'm told by other people that in the future, computing will be done in the cloud. Cloud computing is pretty awesome. You get this illusion of infinite resources, but you only pay for resources used. Quick scaling. Obviously, there are these major companies, Amazons and Microsofts and Googles of the world, that are developing cloud computing technologies for outsourced computation. So that's all very nice. It's very conceivable that data analysis will be done on these platforms. So how do we combine these computation platforms with privacy? So there exist very popular frameworks to ease cloud programming. One of the most famous ones is MapReduce, which is a way of doing parallel processing on these big clusters of machines, and it's been successfully used for things like data mining and genomic computation and social networks and so forth. What we try to do in that work is to try to take this MapReduce paradigm and apply it to this programming model where there are millions of records, what have you, shopping transactions and click streams and so on, and third parties need to be mining this data. And of course, the naive way of doing it is anonymizing the data and giving it to third parties. Well, as I tried to convince you earlier this morning, this is unlikely to work. So how to do it without actually anonymizing and disclosing the data? And one example of this might be healthcare data sets, when there is a huge incentive to contribute data, because it varies from kind of personal incentives like cheaper insurance, but even things like researching new drugs and distributed biomedical studies and stuff like this. But of course, there are huge privacy issues. Okay, so what if somebody learns something? What if insurance company increases my premium? What if life insurance company denies coverage because they see something in the data? So the problem here is how to do computation on somebody else's data given this cloud computing paradigm. Obviously, just running an untrusted program, it doesn't matter, MapReduce or not, running an untrusted program on this data could result in all sorts of information leaks because it's looking at the data and who knows what information it's exfiltrating or what it's trying to learn from the data. So the whole purpose of this line of research is try to prevent these things from happening. One naive answer, you could try to audit the data, audit the program to make sure it's not exfiltrating information about the data. But this is hard because source code of the program might not even be available. Ideally, we would work in a setting where the code is black box. We don't have to look at the code. And also, how do you know even what the program is doing? General program analysis, try to figure out what it's doing is very hard. So we'll go for the low-hanging fruit here and try to build a system for privacy-preserving computation that confines untrusted program and allows them to operate on trusted data in a privacy-preserving fashion. And this is the system called Aravat that we developed a few years ago and try to evangelize a little bit, like I said, with intermittent success. And that's a framework for privacy-preserving MapReduce computations with untrusted code. So this is the vision for this work. This is not what it ended up doing, but the vision for this is what could Netflix have done, if they did this right, if you will. So maybe they, instead of publishing the data, they would have provided some platform where people can run their code against the data and learn useful things from it without violating privacy of individual users whose data is being analyzed. And the privacy guarantee that we're going to give here is differential privacy. That is, we'll try to provide a bound on the information leak in the differentially private sense that I'll make more precise in a moment about an individual's data. So background for this is MapReduce, which is this very popular, as I mentioned, computing paradigm. So, this is just a brief kind of, 2-minute tutorial in MapReduce, which is really quite simple. So the idea is that you have this massively distributed independent computations called mappers, and the data is split and sent to different mappers. They compute something on it. Then the outputs are combined during the reduce phase and computed. So basically, this is a way of taking advantage of massive parallelism. So here is an example of computing a number of iPads sold. So mappers take an input, and each mapper obviously looks only at some subset of the input, and then it just computes the number of iPads sold in its little chunk of the inputs. Then these partial outputs are all assembled in the reducer, which computes the sum of them and produces the total number of iPads sold. Okay, really very basic kind of paradigm. So what we'll try to do is build privacy-preserving computation using that as the underlying medium. And you can see how these mappers work. So like on the first one, the answer is going to be 1. The second record goes to the second mapper, and that's not going to produce any output or produce output of 0. And the last 2 records go to the third mapper that produces the count of 1. And then these counts are combined by the reducer and computed and summed up to 2. All right. So in our model, we will assume that the underlying cloud infrastructure, hardware, virtual machines, and so on are secure. To implement this, we had to modify the MapReduce framework, and we rely on kind of standard Hadoop distributed file system and some modifications to Java virtual machine and some access control for SE Linux. So these are a bunch of kind of system-C aspects, which are kind of not very interesting by themselves, but it turns out that if you're trying to build a system that actually runs and does something, you spend much more time doing this than kind of thinking about conceptual issues. Anyway, so kind of had to do this. Then once you have this trusted platform that we're providing, the idea is that data is being uploaded into this framework and into these distributed file systems. And it's important to the privacy provider, for the data provider to set up certain privacy parameters, okay? And this is a feature of differential privacy that it's only usable if you specify certain parameters. And let me invite you not to think about it now, okay? It's just some parameters that you need to specify, okay? Do not worry about it, nothing to see here, move along, okay? So the data provider uploads the data, and then the computation provider implements whatever data analysis they want to do, whatever algorithm, they write it as code. And actually, our system is designed to accept black box Java code. So the computation provider just uploads a Java program into the system, and this Java program does whatever data mining it needs to do, and then will magically provide privacy for the output. So isn't that nice, okay? You upload the data, somebody uploads the code computes on the data, and in the end, the output is privacy preserving. Well, that's the vision. The reality is a little bit messy. So we have to deal with the fact that this code is potentially malicious, okay? So it's possible, that's the whole point here, is try to prevent a potentially malicious potentially malicious computation provider from learning things about the data that they aren't supposed to learn. And the leaks we're concerned about are kind of standard leaks via storage channels. So, what is to prevent a computation provider, maybe his program just reads private data and sends it over the network, or stores it into a file and then some other program reads it. So that would be bad. But we're also concerned, this could leak out. So that problem we will solve with access control. But also there is another one, leaking via output. And this is a much more subtle problem because a malicious program could be written in a way that looks at the input and then somehow modulates its output based on what it sees in the input. Maybe it looks at it, and if it sees some secret, it outputs 1 million. Otherwise, it outputs 0. In this way, even though there is no direct flow of sensitive information from the input to the output, there is an indirect flow. That is, the output of this computation is dependent on the input, and this is another way of leaking information about sensitive inputs that you have to somehow deal with. And to prevent this kind of leakage, we will try to use differential privacy here. So this system basically uses two mechanisms: mandatory access control, which prevents leaks through storage channels, network connections, and so on. That's kind of the systems part of it. And differential privacy, which prevents leaks through the output of the computation itself. So prevents algorithmic leaks. In order to do this, we have to restrict the expressiveness of the code. In particular, we allow mappers to be arbitrary, untrusted. Could be any Java code, but we're going to enforce certain constraints on it. And we provide a very limited menu of kind of stock trusted reducers. So they're provided by the platform, and we cannot allow the program to use its own reducers because otherwise it becomes an information leak. So it has to use one of our reducers, and these are things like summing. Basically, these are aggregation operators like summing, counting, and so on. And these are provided by us, and this is where privacy enforcement will actually be done. All right, so untrusted mappers running in our system are confined using a bunch of kind of systems and mechanisms that are not maybe necessarily interesting by themselves, but need to be done in order for this to be secure. So the whole thing runs on SE Linux. And these things are labeled to restrict interactions. In particular, untrusted mappers cannot talk to each other. They're denied network access. Their file system interaction is very limited. So that's all very nice. Unfortunately, in any real system like this, you have to deal with the possibility of side channels because this is untrusted code, and which has access to sensitive data. And unless you are very, very careful, it has ways of signaling information about what it sees. And in our design, we thought we enumerated all side channels, but then a few years after we published the paper, it turned out that it does contain certain leakages via side channels. In particular, they're not allowed to access they're not allowed to write files that are readable by others and things like this. So, but the problem is, what do you do if they try to access it? So what's kind of a natural reaction? So you try to confine, make sure something cannot write a world readable file. So what do you do if it tries to do it? Kill it? Well, killing it would be nice. Unfortunately, we did something a little stupider. So if you don't kill it, what do you do? What? Sorry, I couldn't hear. Yeah, well, I mean, like a natural way is to throw an exception, right? So, I mean, it did something bad, so you throw an exception. Unfortunately, if it does something bad and you throw an exception, that becomes a signaling mechanism. So the code runs normally, and then it sees some secret, and then oh, I want to signal that I saw something embarrassing in the data. Let me do something that's forbidden. So that the system throws an exception, and that becomes a way of that code of signaling that even though it has no way of exfiltrating the data, it's still a communication channel. It's like every time I want to signal something to my master, I'm going to do something forbidden, and then the system will throw an exception. So you have to be very careful generating exceptions. You have to kill things silently without generating exceptions. Otherwise, it becomes a leakage channel. So, but access control is not enough. So access control gives us a way of tracking the flow of the data, but every time you do an aggregate computation, like suppose you're computing some average, you do some data mining, the output depends on all inputs. Like if you're computing this, so effectively, so far access control, I mean, it made sure that it doesn't leave copies of the data lying around, but you still end up with an output that depends on all inputs. So how do you know that it's safe to publish this output? How do you know that it's not leaking too much information about any of its individual inputs? Because that's the really hard problem there. So making sure that the computation as it proceeds doesn't leave any copies of the data lying around, that's kind of painful technically, but for this, like, there are easy solutions. But now you have the problem, okay, so you computed something, you process data in all sorts of ways, and now you want to publish the result. So when is it safe to publish the result?
You eliminate one of the players or any of the players, and the results remain.
Effectively, what you need is something like differential privacy. You want to say that if the result is differentially private, it's okay to publish. What does it mean that it's differentially private? It doesn't depend too much on any particular input. That the same output would have been produced with a similar probability even if this record wasn't there, or even if that record wasn't there. So it's safe to publish if the output is differentially private. So, and what do you want to, and what this allows you to do, I mean, I haven't even told you so far how you achieve differential privacy. This is just an intuition why you need it, because if you don't have it, then it's possible that, you know, untrusted code could be signaling things in a weird way. It could be producing certain counts based on what it saw in the output, in the input, and so on. So if you just publish the result, that could leak information. So what you need to make sure that the output is not leaking any particular input, you need to make sure it's differential private. So let me go back again to differential privacy and remind you of this intuitive definition. So the intuition here is the mechanism is differentially private if any output is produced with similar probability, whether any given input is included or not. And you get a bounded privacy loss if effectively for every participant. Somewhat subtle notion, but it's the only one we've got, so that's what we'll try to achieve here. So there are many differential algorithms and mechanisms for achieving differential privacy in the literature. Here we're going to go for the simplest one based on adding random noise. So instead of outputting the true output, we're going to perturb it by adding some random noise. But here is a key question. So how much random noise should we add intuitively? How, like, so the way privacy is going to be achieved, we're going to perturb the output a little bit to hide the presence of any individual. So, but how much noise should we be adding? What do you think? Just intuitively, given what we are trying to achieve.
Order of the user.
Well, all right, I mean, I don't even mean mathematically, okay? Just intuitively. So somehow we need to add enough noise to mask the influence of any given input, right? So, and this is related to, what do you think this is related to? Well, let's be intuitive here. So suppose I'm computing a constant function. How much noise do I need to add to a constant function to hide the presence of any input? None, because the output of that function is actually independent of any input, right? But suppose, so you see what I'm getting at. Somehow the amount of noise depends on how much the output depends, it's related to the function you're computing. So the technical term for it is sensitivity. So how sensitive the output of the function is to any input, to any particular input that you have. So this is what's known function sensitivity, which is the maximum effect of any single input on the output. For example, like average height of people in this room has low sensitivity because, you know, we don't have any basketball players here. So any single person's height doesn't affect the average by too much. So effectively, to hide the presence or absence of an input, you need to, well, presence and absence is not quite correct. To hide the influence of an input, you need to mask this effect. And what's very important is that sensitivity depends on all possible inputs, not just on the current input instance. So you have to look not at the particular data set you're computing on, you have to look at the entire domain of the function and then measure sensitivity over the entire domain. This is a kind of subtle point that you have to account for. Okay? So for example, if we computing a sum of values, then the maximum effect of any input element is what? The biggest element in the domain. Why? Yeah?
Is there an assumption that you can ask the function only once?
Well, Okay, you're going to incur a certain privacy loss on every question, and then they're going to accumulate, okay? So you can ask multiple times, but every question bears a certain privacy cost. And this is something that I'm trying to sweep under the rug kind of very hard here, okay? Because once we start talking about this, we'll never finish, because you'll ask me, what's an acceptable loss? When can I stop? And these are all kinds of unpleasant questions that nobody wants to discuss here. So I'm trying to present a very beautiful picture here where we're not talking about these questions. So, all right. So why, do you see why the sensitivity of the sum of elements from a fixed domain as the maximum element of the domain is because in the worst case, if you remove, if the difference of the value of the sum between a data set or the maximum element is present and it's absent is exactly equal to that element. Okay, so this is all very good. And I mean, I'm trying to give here a very kind of intuitive explanation of how the theory works. But we have like kind of a problem here in this system that I described. That it's all very nice that we add noise proportional to sensitivity, but we cannot apply it directly here. Do you see why not? So this is actually a kind of a challenge. Why can't you not just add noise proportional to sensitivity in our system that I described? What? Yeah, and how do you calculate the sensitivity? You don't even know what you're computing. Like our whole point here was supporting black box code. So somebody gave you a chunk of code. How do I know its sensitivity? I don't know. I mean, like this whole thing assumes that I know the function being computed, but here I don't know the function being computed. So that's a bit of a challenge. So that's the mechanism we'd like to use. I mean, this is known as Laplacian mechanism. So where you add exponential noise to mask the effect of a single input, but applying it in our case is a problem because we don't know the sensitivity. And the way we get around it is we require the computation provider to declare the range of possible outputs that his mappers can produce in advance. Before code touches the data, he has to say, my mappers can only produce values in a particular range. And we use that declaration to estimate sensitivity. Yeah, question?
So let's say the piece of code asks for the average height of persons about that are older than 70 years old.
Right.
And the range is 0 to 2 meters.
Yeah. So,
how would you compute the sensitivity?
well, we would know that the output cannot go, we would assume that the sensitivity is 2 meters. We would assume that it's equal to the size of the declared range. That's actually an overestimate of sensitivity. It's a conservative overestimate. Do you see why it's an overestimate? Why it's different from?
Because you can always say, calculate between 0 and 2000, and the result will always be around 100. And he wouldn't, between 0 and 100, he wouldn't catch it.
Actually, I mean, we will. No, I don't.
So the problem here is not the sensitivity. The problem is, let's say, if the age was 100. Right?
Yeah.
And the interesting information is whether or not there is somebody that's older than 100 here. I don't care about the age. Let's say the question, I'm trying to figure out if there is somebody that's older than 100 in this audience.
Right.
And the question I present to the system is whether or not, please compute the average height
Right.
of all persons above 100.
Right. Sure.
Over a certain quantity, you would get 6 feet under in any case.
So, yeah. So that's the height. Okay. No. I mean, I think that's not the problem here. So we can still handle that. So you just need to declare the range of outputs, and it would still work.
But the range of output would be the same whether or not it's...
That's right. I mean, it's in some sense it's bigger than the true sensitivity. So we will be adding too much noise. but it's still a safe thing to do. What I'm getting at here, the reason it's a conservative overestimate is because the range captures the difference between, so sensitivity is the difference between outputs on data sets that vary in one person. But the range is the difference between any two data sets, okay? Could be differing on more people. So it certainly includes the difference on one person. But because, in fact, this is bigger than the true sensitivity, because of that, we will be adding too much noise, possibly, and the results might not be useful. I mean, it's subtle. Sorry, I mean, there is certain subtlety here, and so on. But that gives us a conservative overestimate. And by the way, what do we need to do if a mapper produces an output that lies outside the range?
We estimate the range.
What?
You have to recalibrate.
No. The range has to be declared in advance. And then the output said, I'm going to only output numbers between 0 and 100. And then, boom, it outputs 200. What do?
You have to pick a random output, not to allow signaling through that.
Right. So the naive answer would be, oh, I throw an exception because it went outside the range. But you cannot do this, right? Because that becomes an information leakage. So effectively, you have to silently produce a fake output that runs inside the range, which means that if the mapper code is buggy, if the provider accidentally declared the range that's wrong, will the provider ever learn that his code is producing bogus results? You cannot even let him know because that becomes a leakage. That's why these things are kind of so subtle. Anyway, almost done here. So yeah, a malicious mapper might output values outside the range, but if it produces value outside the range, then you silently replace it by a value inside the range, and you do not notify the user, otherwise it becomes a possible leak. And here is how it works. So you have range enforcers on mappers. They ensure that all values that come out of it are lie inside the declared range. Then these things go into one of the trusted reducers, which adds noise. And the amount of noise that is being added is proportional not to the true sensitivity of the code, but to the declared range of outputs, which is an overestimate of sensitivity. So this is a very kind of hairy, complex way of doing it, but it's the best we've got. And then when you produce the results are differentially private. So for sensitivity estimates to be correct, it's important that all mapper invocations are independent, or sensitivity estimates are wrong. It is not possible to store an input and use it later. Complicated. And it also limits usability to some extent, but we don't know how to do it better. And like I said, we had a bug, because when enforcing mapper independence with Java virtual machines, if mappers try to not be independent, instead of just silently killing them on doing something, we throw an exception which turns into a side channel, meaning that a code can signal something, at least in the original version of our system, by doing this. Also, it turned out that we were adding noise incorrectly. Anyway, this is really hard to do. It's, what can I say? Once you try to port these theoretical frameworks into working systems, all kind of issues come up that sort of don't matter in theory, but matter in practice. So, sorry. So what can we do with this? Well, we have a small selection of trusted stock reducers, and it turns out that it's sufficient for simple data mining algorithms, sums, counts, thresholds, and so on. If mappers are trusted, in which case we have actually true sensitivity estimates, then more general computations are possible, and so on. But even with these conservative estimates, for a lot of at least basic statistical computations, we could do them well. But here is the thing. So remember I mentioned these differential privacy parameters. I tried to go through this whole part of the talk, which is almost over, and we can go to lunch, without actually mentioning the most important thing about differential privacy, is that it's all very nice that it gives you an output that doesn't depend too much on any input, but the question is, how much is too much? And differential privacy has this parameter called epsilon. It controls the trade-off between privacy and accuracy in each computation. So the smaller the value of epsilon, the more privacy you get, basically the more noise you add, and the results become more private and less useful because they're perturbed by more. And this is just a knob that you can turn, and you, as a user, you get to choose the setting. There is also the concept of the privacy budget. It basically comes from the fact that every time you do a differentially private computation, you pay this epsilon cost, and these are additive. So you do more and more computations, you do repeated invocations, and these epsilons add up until you run out of your privacy budget. And if you try to go and evangelize a system like this, or Pink, or a similar system, and try to deploy it to users, very soon users start asking you, oh, what value of epsilon should I use? What should be my privacy budget? How should I set these parameters? And so on and so forth. And these are very nice questions. Okay? These are very important questions for any practical use of the system. And it turns out that in any real-world deployment or attempted deployment in differential privacy, providing guidance on these questions is maybe the most important task. And these are not the droids you're looking for. Okay? So this is not a topic for this talk. So at this point, I suggest we break for lunch. And when we reconvene, I will talk about kind of challenges for future privacy research and the kind of privacy technologies that are important now and that I'm working on these days. Thanks.